This is a mini lesson for simplifying cube roots. Before watching the video, you should have already done the do now, and if you haven't, please do so now and pause the video. We already know how to simplify square roots. The square root of 24 is 2 root 6 because the square root of 24 is the square root of 4, the biggest perfect square factor, times the square root of 6. We also could choose to use this strategy where we write out all of our factors and then we figure out what factor appears twice for something squared. Similarly, for the square root of 54, we get 3 root 6 from the square root of 9 times the square root of 6, or we see two factors of 3. And the square root of 81 is 9. 81 is a perfect square, and if we weren't sure, we could write 81 as the prime factors 3 times 3 times 3 times 3, and all of our factors pair up, so we have a 3 squared and another 3 squared. We see something similar with variables. So in the first problem here, we have the square root of x squared, and so we're always saying, what could I fill in here? I could fill in x, and the square root cancels with the squared, so we are just left with the square root of x squared being x. We see that in this entire row, because the index is 2 and the exponents are divisible by 2, we don't have anything left in our radicand. So we have the square root of x to the 6th is x to the 3rd, and the square root of x to the 18th is x to the 9th. We could think of this as filling in x cubed squared for x to the 6th, where these cancel, and x to the 9th squared for x to the 18th, where these cancel. Or you could imagine writing out all of your x's. I'm not going to write out 18 x's, but I will write out the 6 of them here, just to visually show you that we would have 1, 2, 3 sets of 2 x's, so I would have an x to the 3rd and nothing left in the radicand. In the next row here, since my exponents are odd, that wouldn't be the case. So for x to the 3rd, I get x root x because I have an x squared, but I also have an x in my radicand. So the square root of x squared cancels and gives me an x as a coefficient, but I still have another x left over in my radicand. If you want to write out all of your prime factors, we'd have 3 factors of x, and we could circle 2 of them, and then we'd have 1 x left over in the radicand. Similarly, x to the 11th, the square root of x to the 11th is x to the 5th root x, because we end up with x to the 5th squared times another square root of x. And so although we're going to cancel these here and get a coefficient of x to the 5th, we would still have an x left inside. And the shortcut for this is to do 11 divided by the index of 2 to get our 5, and we have a remainder of 1 inside. I could write out 11 factors of x, circle 5 groups or pairs of them, and be left with 1 left over. And lastly, the square root of x to the 15th, we get x to the 7th times x, because 15 divided by 2 is 7. We have 7 pairs of x's in the radicand and 1 x left over that would stay in the radicand. So now let's move on to when we have cube roots. So we're now looking for the biggest perfect cube factor that goes into our radicand, both with numbers and with variables. So I wrote out the perfect cubes that I know here. And so if I have the cube root of 24, I could say, well, 8 is the biggest perfect cube factor of 24. So I'll break this down into the cube root of 8 times the cube root of 3. That is 2 times the cube root of 3. Don't forget that we should make sure that we have this index written here. And if we want to check this, we could cube the coefficient and get 8 and put it back inside. So we would have the cube root of 24. Although my prime factor breakdown is the same as before, this is 2 times 2 times 2 times 3, I'm now looking for a set of 3 factors inside because I'm looking for a perfect cube. On the next problem, I have the cube root of negative 54. Since it's a cube root, I can take a negative, and the negative I'm just going to write out front at the start so I don't forget. And that's because negative 1 cubed is negative 1, so the cube root of negative 1 is negative 1. And then I know that 54, the biggest perfect cube factor that goes into that, is 27. So I have the cube root of 27 times the cube root of 2. That gives me 3 times the cube root of 2. In this case, negative 3 times the cube root of 2. I could write out all of my factors. If I look back up above to see its prime factorization here, I'd be circling 3 3s, and so I'd have a 2 left inside, and I'd have 1 factor of 3 on the outside as a coefficient. 81, well, the biggest perfect cube that goes into 81 is again 27, and so this time it's the cube root of 27 times the cube root of 3, so I have the cube root, or 3 times the cube root of 3. If I wrote out all of my factors, 81 is 3 times 3 times 3 times 3, and so I would pull out one of those sets of 3 3s, and I'd still have a 3 left in my radicand. We're going to use our same patterns that we saw before that are listed at the bottom here, if you're looking for them in writing, to simplify these cube roots with variables. So I can basically take my index and I can divide my exponent by my index. So if I have the cube root of x to the 6th, I know that that will be x squared. I could do 6 divided by 3. It goes in evenly. If I'd like to see y, I'd say the cube root of what cubed. I can fill in an x squared here. This is the cube root of x to the 6th because I'll multiply those exponents and these cancel. Or again, I could write out 1, 2, 3, 4, 5, 6 factors of x, and I'm not looking for pairs. I'm actually looking for groups of 3 here. There are none left over. In the next problem, I will pull out a negative right at the start, and then since I have an x to the 4th, I know that that is x to the 3rd times another x, and so I could show that out, or I could do it in my head. So I divided 4 by the index of 3. I had 1 x on the outside. I'm left with 1 inside. Y to the 12th, y to the 4th will go on the outside because I would have 4 groups that each have 3 factors of y. In other words, 12 divided by 3 gave me that 4 there. If you would like to write out all of your factors, you can. If you'd like to do kind of an in-between step where you write out the cube root of -1, the cube root of x to the 3rd, and then you have this extra x to the 1st, and then the cube root of either y to the 12th, or you could write y to the 4th to the 3rd if that's something that works better for you. We have all these different strategies. You just need to find what works for you. And then the last problem, I can see that these exponents are much too big for me to want to write out all 23 factors, so I'm definitely going to be using these strategies. 27 is a perfect cube, so I have a 3 on the outside, and I'm going to start by writing a cube root symbol so I can start filling in my values in my coefficient and in my radicand. X to the 9th, 9 divided by 3 goes in evenly, so I'd get 3 factors of x on the outside. That makes sense because x to the 3rd is x to the 9th. Y to the 16th, 16 divided by 3 is 5 with a remainder of 1. So in other words, the x to the 5th would give me 15 x's when I cube it, but I still have another y left over. Then I have z to the 23rd, 23 divided by 3 is 7. That uses up 21 of my z's, and I'm left with 2 z's left in the radicand.